their cache array. So the cache array of a level 1 node will now be of size 2. So at this point the cache here is full. Let me denote a full cache by a circle, and a node that has finished emitting all its cache elements upwards is represented by a square, let us say. So all level 1 nodes have just become full. In stage 2, in stage 4, again this is a dummy stage because nothing happens. In stage 5, level 1 nodes will emit every second element into the sample. So the sample will have a size of 2. Now once the sample array has a size of has something in it, these will merge to form the cache array at the parent. So at the parent now we have something in the cache. So the cache size at the parent is 2, but mind you, the parent hasn't become full yet. So let me mark every 3 steps, because that's when one level becomes full. In the 6th stage, the level 1 nodes will emit all their cache elements into their caches, into their samples, and therefore become dead from here onwards. The size of the cache at the parents will now be 4. Still there is no sample because the samples were to be drawn from 2 elements, therefore nothing could be drawn. In step 6, this is how the size of the sample array and the cache array would be. In stage 7, first let us see how the sampling will be done. A level 2 node will be picking every 4th element as a sample. Therefore, we will have a sample of size 1 here. This has already become full. Therefore, here we have 1, 4. Since the sample array is filled, now at the 3rd level we will have something in the cache. There will be 2 elements in the cache. In the 8th stage, level 2 nodes will pick every second element into the sample. So now there are 4 elements, so you will get 2 elements in the sample array. The level 3 node cannot pick any sample because it's still picking every 4th element, but its cache array now becomes bigger. It will have four elements here. Now coming to the 9th stage, at this point the level 2 nodes will emit all its cache elements into the sample array. The level 3 nodes will pick a sample, therefore they will have a sample array of size 1, and of course above that, since there is nothing in the cache, there is nothing in the sample as well. So we decide on the samples in this fashion. Then we can decide on what the size of the cache will be. The cache will be the 2 samples of the children merged. Therefore here we will have 8, which is 4 plus 4, and here we will have 2, which is 1 plus 1. So this node has become dead now because it has emitted all its cache elements into the sample, and this has just become full. So at the 3rd stage, level 3 nodes have become full. Now we come to the 10th stage. In the 10th stage, first we draw the samples. From 2 we cannot draw any sample, so there is no sample here. From 8 we will be picking every 4th element as a sample, so we get 2 elements. So the cache sizes will be like this: 2, 8 and 0, 4 sample and cache sizes. Level 3 nodes are already full. They became full by the 9th step. Then when we come to the 11th stage, there will be samples drawn. At the 5th level there will be no sample to be drawn. At the 4th level we will have a sample size of 1, because we are picking every 4th element, so out of 4 1 will come. And at the 3rd level we will be picking every second element, so we will be picking 4 elements into the sample. So the cache sizes are like this. At level 3 the cache size is 8, it's already full, so it's not going to change anymore. At level 4 we have 8 again, because the sample arrays of the children are of size 4 each, and at the 5th level we have a sample size of 2. So that is how the sizes look in stage 11. Now we come to the 12th stage. In the 12th stage, when we draw the samples here, we find that the level 3 node gets all the cache elements into the sample array, and therefore it becomes dead hereafter. Then the other samples would be like this. At the level 4 nodes, we pick every fourth element, so we get a sample size of 2. And here, of course, we are still continuing to get a sample size of 0. So the cache sizes would be 2 plus 2, 4 here, and 8 plus 8, 16 here. This has just become full. The level 4 node has become full just now. Now when we come to the 13th stage, in the 13th stage we have to pick every fourth element at this node, so we get 4 elements, and every fourth element here again, so we get 1 element here, and above that we of course don't have anything to pick. At level 6 we have 0 elements. So the cache sizes would be 2 here, 8 here, and 16 here, of course. So that is how the sizes would look like in stage 13. When we come to stage 14, here we would be picking 8 elements into the sample. Every second element from the right hand side is picked, so the sample size would be 8. Here we are picking every fourth element, so out of 8 we are getting 2 elements, and here we will not be able to pick anything, so here the sample size continues to be 2. But the cache size will be 2 plus 2, 4 here, and 8 plus 8, 16 here. Now finally when we come to the 15th stage, here we will be picking every element into the sample, and here we are picking every fourth element into the sample, and here we will be picking 1 element into the sample, every fourth again, and here of course the 7th level has not opened, therefore its cache size is 0, but now it's going to get the sample size is 0, but now it is going to get 2 elements in the cache, and here we will get 4 plus 4, 8, and here we will get 32, which is 16 plus 16, and this of course had already become full, so this node becomes dead now. So in the 15th stage, the 5th level node becomes full. So this is how the cache and sample sizes vary through the stages. So now let us make some observations. In stage numbers of the form 3R, that is stage numbers which are multiples of 3, for example when we consider 15, we find that the cache sizes are decreasing 32, 8 and 2. For example, in the 15th stage, the cache sizes are going 32, 8 and 2, which means the cache sizes are falling by a factor of 4 as you go from children to the parents. Therefore, the total cache size at the parent is 1/8 of what it is at the children. That is when you put both the children together. So what we find is that the total cache size at the parents level is 1/8 of the total cache size at the children's level. So if you start from the bottommost live level, there are n elements in the cache there. They are all the full nodes. Therefore, above this we will have n by 8 elements. Above this we will have n by 64 elements and so on. Therefore, if you sum the total number of the elements in the cache arrays would be, that is the total size of all the cache arrays put together will be n plus n by 8 plus n by 64 plus etc. all the way to the top of the tree, which we know is less than 8n by 7, which is order of n. So in stages that are multiples of 3, the total cache size would be order of n. Now let us consider stages, stage numbers that are 1 modulo 3, that are of the form 3r plus 1 for some integer r. So in particular, if I consider stage 13, we find that the cache sizes are decreasing from 16 to 8 to 2, 16 to 8 to 2. The cache sizes are decreasing from 16 to 8 to 2. Which means we can generalize this to note that from the bottommost level to the next level, there is a reduction in size by half. After that, we have reduction by a factor of 1/4. Therefore, the total number of cache elements in the live band would be n plus n by 2. At the next higher level, you will have a total number of cache elements which is n by 2. After that, it is division by 8, because the factor 1/4 is for a child to parent, but when two children are put together, we have a factor of 8. And so on. Sorry, here it would be n by 4, and here it would be n by 32, here it would be n by 256, and so on, which is less than 9n by 7, which is again order n. So the total cache size of all the live band vertices put together is order of n in stages that are numbered 1 modulo 3. So when we come to the remaining stages, in stages that are 2 modulo 3, again looking at the pictures, we find that, let us take the 14th stage. Here we find that the cache at level 4 has a size of 16, at level 5 again has a size of 16, and after that it is falling by a factor of 4. So we will have a factor of 1 followed by factors of 1/4. Therefore, if you consider the parent to, when both the children are put together, first we will have half, then 1/8, then 1/8, and so on. Which means at the lowest level we have a total of n cache elements, at the next level we have n by 2, then we have n by 16, then n by 128, etc. So when you add up all the number of cache elements, you find that the sum is again order of n. This is 11n by 7, which is again order of n. So what we have established is that the total number of cache elements in all the vertices of the live band would be order of n. A similar analysis for the sample elements will also show that the total number of elements in all the sample arrays is order of n. So this part I am leaving to you as an exercise, and I would also like you to do this formally. Write a formal proof. Here of course we have looked at this example and have generalize from this, but formally prove that in all stages that are numbered with multiples of 3, the cache sizes would decrease by a factor of 4 as we go up, and similarly for the other stages. So this establishes that Coles merge sort on inputs of size n runs in order log n time using n processors, so that the cost of the algorithm is order of n log n. The CR-EWP for the same complexity. That is, n numbers can be sorted on an ER-EWP RAM in order of log n time using n processors. The ER-EW version is outside the scope of this course, so we will not be discussing this. But can we do faster? As it happens, we cannot do faster, because the comparison complexity of the problem stipulates that you require omega log n time with n processors, or with even a polynomial number of processors. You will not be able to beat the bound of log n even with a polynomial number of processors. So let us prove this lower bound now. A lower bound for comparison based sorting. You are aware of the sequential lower bound, which establishes that to sort n elements using comparisons, you require omega n log n time We prove this lower bound using decision trees. The proof uses the fact that any comparison based sorting algorithm can be translated into a decision tree. For example, when you have a bubble sort implementation for size n, let us say, we are considering the algorithm for an input of size n. So in bubble sort, what we do is this: we consider an array of size n, we assume the elements are given vertically. So in bubble sort, we compare the two lowest elements first, and then we perform a comparison and exchange if necessary. That is, if the smaller element happens to be at the bottom, we swap. Then we compare the next two positions and perform a swap if necessary. By doing this, when we have completed one pass, the smallest element would have reached the top. Therefore, we can draw a decision tree if we have, for example, let us consider an input of size 3. On bubble sort, we go like this: when we have 3 elements A, B, C, the first two to be compared are A and B. If A is less than B, we do something. If A is greater than B, we do something else. If A happens to be less than B, we swap them. So we will have the order C, A, B. If it is not, we do not perform a swap, and we will have to continue dealing with the original order C, B, A. And then we compare the second element with the third element. So in this case, we will be comparing A with C. In this case, we will be comparing B with C, and so on we continue to generate the tree. So given a comparison based algorithm, you can draw a decision tree in this manner. In particular, what you have to observe here is that the first comparison to be performed is hard coded in the algorithm. For example, in the case of bubble sort, we compare the two bottommost elements. These are the two elements to be compared first, irrespective of the input. So this is a fact that is hard coded in the algorithm. In the case of insertion sort, we would be comparing the two leftmost elements. In the case of merge sort, merge sort is a divide and conquer algorithm. So you divide the array into two halves and then recursively invoke sorting on each half, and then again we recursively invoke sorting on further halvings and so on. So if the recursion always prefers left over right, that is, if the left half is executed first, then we would be moving to the left. So we would end up comparing the two leftmost elements again. If we execute the standard version of quicksort, where always the leftmost element is picked as the pivot, the first comparison to be performed is between the pivot and the leftmost of the remaining. So for each comparison based sorting algorithm, the first pair of elements to be compared is fixed, and based on the outcome of this first comparison, the remaining comparisons will be done. Now this essentially gives us an idea about how the proof for the parallel sorting should be devised. To devise a lower bound for the parallel sorting algorithms, we introduce a model called the parallel comparison model. In the parallel comparison model, only comparisons count. What we assume is that apart from comparisons of the key values involved, every other operation has zero cost and takes zero time. This is a simplification that we make for devising lower bounds. Once we devise a lower bound on a parallel comparison model, it should apply to the other PRAM models that we are talking about. This is because a parallel comparison model is at least as strong as a priority CRCW PRAM. How is this so? It can be seen like this. Consider one step of the priority CRCW PRAM. In this one step, various processes want to write in various locations. So let us we sort the processors on the addresses we want to write. Once we do this, all the processes that want to write in the same memory location will come together. For example, let us say the number of processes want to write in location 4. So we will have several processors all wanting to write in location 4 coming together. Then we will have several other processes wanting to write in a larger memory location. For example, let us say these want to write in location 6 and so on. So the processors will be grouped by the location in which they want to write. That is, if we sort the processors on the addresses in which they want to write, we will get the processors that want to write in the same memory location together. But how much time will this sorting take on a parallel comparison model? The sorting will take 0 time. Because what we do here is radix sort. Radix sort doesn't compare the key values. What we have to sort are a set of integers. These are the address values into which the processors want to write. So we sort the processors on these addresses that are integers. We can effect the sort using radix sort. And since radix sort doesn't use comparisons, this can be achieved in 0 time at 0 cost. So what we assume is that the processors are all sorted on the address into which. Now all the processors that want to write in location 4 have come together. All we have to do is to pick the smallest among them. In fact, if we had sorted on the ordered pair, which is the address and the processor number, then we would have the processors in the increasing order of their indices. For example, we would have P3, P4, P7, P9 in this order, because we are effectively sorting the ordered pairs 43, 44, 47, 49. Then we only have to pick the smallest processor index out of all the processors that want to write in the same memory location. So P3 will be selected from this set, P2 will be selected from this set, and so on. So all this selecting of the processors come for free on the parallel comparison model, and therefore the writing itself can be done in order 1 time now after the processors are selected, which means one step of the priority CRCW PRAM can be simulated on a parallel comparison model in order 1 time. What this establishes is that any lower bound that we prove on the parallel comparison model will also apply to all the PRAM models that we have been discussing. Let C of Tn denote the number of comparisons that any algorithm that sorts n numbers in T comparison steps must necessarily perform. CTN is defined like this. Imagine an algorithm that sorts n numbers in T comparison steps. Then the number of comparisons that this algorithm must necessarily perform is what CT of n. That is the minimum number of comparisons that any such algorithm must perform is what CT of n is. Now we claim that CT of n is greater than T times n power 1 plus 1 by T divided by E, where E is the base of natural logarithm, minus Tn. This is what our claim. The proof of the claim will be using induction. So for the basis case, let us consider T equal to 1. Which means we have to sort n items in one single step. we can sort n items in one single step only if we perform all the comparisons at one go. Once all the comparisons are performed, that is every pair of elements are compared with each other, then the rest is only manipulating the comparison data. We don't have to perform any further comparisons. All possible comparisons have been executed. Therefore, if you want to sort n items in one single step, you will have to necessarily perform n into n minus 1 divided by 2 comparisons. If you omit to compare at least one pair, we can prove that the sorting hasn't worked correctly by manipulating the values that you place on these two elements. This you can see is n squared by e. If you put t equal to 1 in this expression, you would get n squared by e minus n. So you can show that n into n minus 1 by 2 is greater than n squared by e minus 1. Therefore, if t equal to 1, our claim is correct. For t greater than or equal, consider C of t1, which means you want to sort one element in t steps. If you have only one element to sort, you don't have to perform any comparison. Therefore, C of t1 equal to 0 for all t greater than or equal to 1. So, if you substitute n equal to 1 in our claim, we find that this is t by e minus t. So, these two will form the basis. So, now let us hypothesize that for all small t less than capital T and n small n less than or equal to capital N, or small t less than or equal to capital T and small n strictly less than n, it is the case that C of T n is greater than T n power 1 plus 1 by T divided by E minus T n. So, this is what our hypothesis is. That is, we are varying n and t both. So, we are considering a particular value of capital N and capital T, and what we assume is that for every small n and every small t, that is at least one of them must be less than or equal to n or t, which means for all these values, for every value within the square, within this rectangle, the hypothesis holds, except for n and t. That is what we want to establish. That is, we consider the rectangle of size n by t, then here all nodes except the bottom right node satisfies the hypothesis, is what we have assumed. So, now let us consider an input of size n and let us assume that an algorithm sorts. Let us say your algorithm sorts this input in t steps. So, this is an adversarial argument. You suggest an algorithm that sorts an input of size n in t steps, capital N and capital T, then I claim that this n and t should satisfy the claim. For this purpose, I, as an adversary of your algorithm, will try to make it work badly. To this end, what I do is this: consider the first step of your algorithm. In the first step of your algorithm, the comparisons that are performed would be hard coded into the algorithm. Exactly as we have seen for the sequential algorithms, here again, whatever be the input, the comparisons that are to be performed in the first step must be hardwired into the algorithm. We construct a graph. In this graph, the vertices are the inputs. Are the input positions. For example, if 6, we take 6 vertices. And if your algorithm specifies that in the first step we will have comparisons between 1 and 4, 1 and 3, 2 and 5 and 2 and 6, then we would form a graph in this manner. In general, we construct a graph in this manner. We take vertices for all input positions and we place an edge between two vertices if elements at those positions are compared in the first step of your algorithm. So in this example, elements at positions 1 and 3 are compared in your algorithm, and elements at positions 1 and 4 and compared in your algorithm, and so on. So after forming this graph, we find a maximal independent set of your graph. Remember, this graph is a function of your algorithm. It is not dependent on the given input, because the pair of elements that are to be compared in the first step is already hardwired in your algorithm. Therefore, this graph is a function of your algorithm alone. Then we find a maximal independent set of this graph. Unique independent set is an independent set is a set of vertices no two of which are adjacent. A maximal independent set is an independent set of an independent set that is maximal. It is maximal in the sense that you cannot add one more vertex to it without violating its independence requirement. That is, for every vertex that is not in the independent set, that vertex is adjacent to some vertex in the independent set. So in this example, 1 and 2 will form a maximal independent set, because the other vertices are all disqualified now from adding to the maximal independent set. For example, if we were to add 3 to the maximal independent set, then there would be a conflict between 1 and 3. So 3 cannot be added. Similarly, 4 also cannot be added. Therefore, this graph has a maximal independent set. 1, 2 is a maximal independent set of this graph. Of course, there could be multiple maximal independent sets for a given graph. So what we have done is to construct this graph based on the algorithm that you have given, and then we have formed a maximal independent set of this graph. After this, let me cook up an input. To make your algorithm perform badly. What we do is this: take n elements from a linearly ordered set. Let us say the size of the maximal independent set of the graph that we have found is x. That is, we have drawn a graph and we have found a maximal independent set in it. Let us say the size of the maximal independent set is x. Then of the n elements that we have taken, place the largest x on the MIS positions. The remaining positions are filled anyhow. What this means is that in our example, the maximal independent set consists of vertices 1 and 2, and we take an input of size 6, some 6 elements that are linearly ordered, and then we place the largest 2 elements at positions 1 and 2. The remaining 4 elements are placed at positions 3, 4, 5, 6. So in general, what would this ensure? On this input, now we run your algorithm. Then what we find is that in the first step, your algorithm doesn't do for sorting the elements that are placed on the maximal independent set. Why is that? Because the elements that are placed on the maximal independent set are not being compared in the first step. The maximal independent set in particular is an independent set, therefore no two vertices belonging to it are adjacent to each other. What it means is that these two are not being compared in the first step. Therefore, these x elements will not be compared with each other. Since we are not comparing these x elements with each other, what it essentially means is that your algorithm is not doing anything towards sorting these x elements. The other comparisons that are being performed will be between these x elements. So here we have a maximal independent set of size x, and here we have the rest of the vertices, which are n minus x in number, and then all the edges in the graph are either between the maximal independent set and the rest. So every edge is either of this form or of this form. There is no edge that is within the maximal independent set. That is, two vertices of the maximal independent set cannot be adjacent to each other. So every edge is of this form. Now, how many such edges could there be? The number of edges between the maximal independent set vertices and the rest should be at least n minus x. Why is that? A vertex that is not in the maximal independent set should be adjacent to at least one vertex in the maximal independent set. If this is not the case, then we would be able to add that to the maximal independent set, and the maximal independent set would no longer be maximal. So the number of edges between the maximal independent set and the rest of the graph is at least n minus x. So in the first step, the algorithm performs these many comparisons, these n minus x comparisons, but these comparisons are all between the largest elements in the set and the rest. But we have purposefully kept the largest elements at these x positions. Therefore, all these comparisons are actually not doing anything towards sorting the elements that are in the maximal independent set or sorting the rest of the elements. So you can say that all these elements are in that sense wasted. Now we have ensured two things. The first step of your algorithm has done nothing towards sorting the MIS elements, and the comparisons between the MIS elements and the other elements do not contribute to the sorting of either set. But then we can give a benefit of doubt to the algorithm. We can assume that all the comparisons that the algorithm has performed within this set, if I call this S and this as u minus S, where u is the set of all the vertices, then any comparison that you perform within u minus S, you can assume is contributing towards the sorting of u minus S. Therefore, u minus S is already on its way to being sorted. So, you can assume that the algorithm has made the best possible progress towards sorting of u minus S. So, this is the benefit of doubt I am giving to your algorithm. In the best possible way. So, with these assumptions, we are now able to write a recurrence relation. We can say that the cost of sorting n elements in t steps is greater than or equal to the cost of sorting n minus x elements in t steps. This is the cost of sorting the set u minus S, in particular when you want to sort S as well as u minus S. But then the algorithm has been given a benefit of doubt, and what we have assumed is that the algorithm is on course to sorting the elements of u minus S in t steps in the best possible way. Therefore, the total number of comparisons the algorithm will perform in sorting these n minus x n minus x. The algorithm has wasted at least n minus x comparisons by comparing elements of the maximal independent set with the rest. Now, when we consider the elements of the set S, we find that no comparison has been performed between these two elements, and we have already lost one step. So, if the algorithm has to finish sorting the entire set in t steps, then this one particular set will have to be sorted in t minus 1 steps, and there are x elements in it. So, this would be the recurrence relation that governs CNT. Once again, the recurrence relation is argued in this fashion. We have to sort the set of size n. Let this set be called U. So, we have to sort the set U. We have separated the set U into two sets, S and U minus S. S is a maximal independent set and U minus is the set of all the remaining vertices. Now, the algorithm has been given the benefit of doubt. What we have assumed is that it has done the best it could towards, so this algorithm is on course to sorting U minus S in t steps. Therefore, the total number of comparisons that the algorithm will be performing within U minus S would be Ct n minus x. The size of U minus S is n minus x, and this is going to be sorted in t steps in the best possible way. So, the total number of comparisons that the perform within U minus S is Ct n minus x. Then the algorithm spends n minus x comparisons between S and U minus S. So, that is what the second term is. So, you can say that this is a set of wasted comparisons because they do not contribute towards sorting either U or U minus S. And then finally, when we look at the set S, we find that the first step hasn't done anything towards sorting S. It has already wasted one step. Now, when the algorithm is over, S will have to be in sorted order. So S will have to be now sorted in t minus 1 steps. So the number of comparisons we will have to perform will be C t minus 1 x. So this is the recurrence relation that governs the number of comparisons that the algorithm must necessarily perform to sort n elements in t steps. Now using the hypothesis, we have assumed that the claim is correct for all ordered pairs where at least one of the components is smaller than the components here. That is, either the first component is less than n or the second component is less than t. That is the case with both of these. So we can substitute n minus x minus n minus x simplifying this expression, we will be able to prove our claim. The rest of the proof we shall see in the next lecture. So that is it from this lecture. Hope to see you in the next lecture. Thank you.
The Kelvin cycle is also known as Kelvin-Benson-Boschem cycle or reductive pentose phosphate cycle or C3 cycle. This cycle was discovered by Melvin Kelvin. It involves a series of biochemical redox reactions that take place in the stroma of chloroplasts in photosynthetic organisms. In the Kelvin cycle, carbon dioxide and water from the environment are enzymatically combined with a 5-carbon acceptor molecule, that's ribulose 1,5-bisphosphate, also called as RUBP, to generate 2 molecules of 3-carbon intermediate. This intermediate, that's 3-phosphoglycerate, it's also called as 3-PGA, is reduced to carbohydrate by use of ATP and NADPH generated photochemically in the light reaction. The cycle is completed by regeneration of the 5-carbon acceptor, that's ribulose 1,5-bisphosphate. Since the input of carbon dioxide is continuous, the synthesis of is the output for maintaining an adequate flow of carbon atoms in the cycle. The Kelvin cycle proceeds in 3 stages. Number 1 is the carboxylation of the carbon dioxide acceptor RUBP, forming 2 molecules of 3-PGA, the first stable intermediate of the Kelvin cycle. Number 2 is the reduction of 3-PGA to glyceraldehyde 3-phosphate, a carbohydrate. And number 3 is the regeneration of the carbon dioxide acceptor RUBP from glyceraldehyde 3-phosphate. A schematic representation of the C3 cycle is as: in the carboxylation phase, carbon dioxide reacts with RUBP, that's ribulose 1,5-bisphosphate, to yield 2 molecules of 3-phosphoglycerate. The reaction is catalyzed by the chloroplast enzyme ribulose bisphosphate carboxylase or oxygenase, referred to by the acronym RIBISCO, through a 2-step reaction. The product of the first step is enediol enzyme complex that can capture carbon dioxide or oxygen. Thus, the enediol complex is the real kinase. The carbon dioxide that is captured by the enediol in second step initially produces a 6-carbon complex, which is an unstable intermediate, that's 2-carboxyl 3-keto arabinolitol 1,5-bisphosphate, that immediately splits into 2 molecules of 3-phosphoglycerate, that is 3-PGA, a 3-carbon compound. Here it is to be noted that the enzyme RIBISCO has both carboxylase and oxygenase activity and is very abundant protein, representative of the total soluble protein of leaves. In the reduction phase of C3 cycle, the 3-phosphoglycerate formed as a result of the carboxylation of RUBP is phosphorylated to 1,3-bisphosphoglycerate, that's 1,3-BPGA. The enzyme 3-phosphoglycerate kinase catalyzes the phosphorylation of 3-PGA by ATP produced during the light reaction. Here it is to be noted that 2 molecules of 3-PGA are produced for every carbon dioxide that enters the cycle. So this step utilizes 2 ATP molecules per molecule of carbon dioxide fixed. Then another enzyme, that is glyceraldehyde 3-phosphate dehydrogenase, catalyzes the reduction of 1,3-BPGA by NADPH, which is another product of light reaction, to glycerol 3-phosphate or 3-phosphoglyceraldehyde, and the NADPH is oxidized to NADP positive. Here again 2 molecules of NADPH are utilized per molecule oxide fixed. The next stage in the Kelvin cycle is the regeneration of RuBP. 5,3-PGAl molecules produce 3 RuBP molecules utilizing 3 molecules of ATP.
Swayam Prabha, Digital India, Educated India.
Hello everyone, welcome to this lecture. So, in this lecture we will see the more efficient solution for the degree reduction problem due to Gennaro-Rabin. This is called as the GRR degree reduction method, and we will also to get a better understanding of the degree reduction method. So, just to quickly recap, this was the BGW reduction method that we had seen in the previous lecture, right, which is done in 2 stages, right. So, let me write down the 2 stages here. So, when you go again, so there is a typo here, I should have used a different variable S1, S2, Si and Sn here. So, in stage 1 we do the randomization, and in stage 2 we do the degree reduction. Okay. The randomization is done by adding shares of 0, random shares of 0 lying on a 2t degree polynomial, and then the degree reduction of that random share of the 2t random sharing, 2t degree random sharing to t degree random sharing happens via truncate operation. Now, what the GRR degree reduction method does is the following: it cleverly combines both these 2 stages in a single same stage. It will be doing the randomization plus the degree reduction, and that is why it is more efficient, right, because if we follow this BGW reduction, then we have to do the interaction both in stage 1 as well as in stage 2, but if we can combine both those 2 stages in a single stage, then the parties need to interact only once, they do not need to interact twice, and that will be saving both in the number of rounds as well as the amount of communication which is needed. Okay, so, let me explain the GRR degree reduction method again. This will require T to be less than n over 2, okay. And as I said earlier, this is a necessary condition not only with respect to the GRR degree reduction method. Later on we will prove formally that any generic MPC protocol, if you want through that, if you want to evaluate securely a multiplication gate, we need this necessary condition of t less than n over 2. Okay. So, in stage to begin with, the parties will first compute a non-random vector of shares of AB lying on a 2t degree polynomial. How they can do that? Just locally multiplying their respective shares of A and B. No communication has happened at this point. Now, the idea is that since t is less than n over 2, that means it's greater than equal to 2t plus 1, okay, and the degree of k polynomial is 2t, and we have more than 2t plus 1 number of shareholders or 2t plus 1 number of shares of this k polynomial available. By the way, I will interchangeably use the term shares of the polynomial or the shares of the value. Both mean the same thing. Shares of the value mean distinct points on the sharing polynomial. When I say shares of the polynomial, by that I also again mean the distinct evaluations of that sharing polynomial. Okay. So, the first thing to observe here is that the constant term of this k polynomial, which is the unknown value a b, is a linear function of this k values k1, k2, ki, kn. This is because if you recall, know that alpha 1 k1, alpha 2, so we know that alpha 1 k1, alpha 2 k2, alpha I ki and alpha n kn, they together interpolate uniquely this kz polynomial. Why uniquely? Because n is greater than equal to 2t plus 1 and the degree of k polynomial is 2t. Okay. And we know the form of k polynomial can be expressed as a in terms of the distinct points on the k polynomials in terms of the delta polynomials. Okay. And if this is the case, then by substituting z equal to 0, I obtain the following relationship. I can say that k of 0 is the delta 1 0 times k 1, delta 2 0 times k 2, delta n 0 times k n. So, now let me call this delta 1 0 to be the constant c 1, delta 2 0 to be the constant c 2 and delta n 0 to be the constant c n. They are basically your Lagrange interpolation coefficients, which we had discussed when we discussed Lagrange polynomial interpolation over the finite fields. Okay. And k of 0 is this a b. Okay. So, the summary here is that unknown a b. Why unknown a b? Because it is secret shared right now through the k polynomial. No one knows the value of a times b, because a was secret shared, b was secret shared, and parties have just applied their respective shares of the a and b. So, what we have summarized here is that based on Lagrange interpolation, we know that this unknown a b, a times b, is a publicly known linear combination unknown values k 1, k 2, k n. Why publicly known? Because the Lagrange coefficients fancy C1, fancy C2 and this fancy Cn, they are publicly known. They have got absolutely nothing to do with your Kn. Okay, because this C1 is delta 1 0 and delta 1 polynomial is basically publicly known. Delta 2 polynomial is publicly known, hence delta 2 0 is publicly known. Delta n polynomial is publicly known, hence delta n of 0 is publicly known. What is not known are the actual k1, k2, kn, not known in the sense it is not publicly known. K1 is available only with P1, K2 is available only with P2, Ki is available only with Pi and Kn is available only with Pn. and we know how to securely compute linear functions of private inputs. What does it mean here and why it is applicable here? So, we are considering right now a scenario where P1 has the value K1, P2 has the value K2, Pi has the value Ki, and Pn has the value Kn. In that sense, they are private inputs of the respective parties, and we know that there is this unknown AB which can be expressed as this public linear function of this private inputs. So, if we ask the parties P1, P2, Pi, Pn to respectively secret share K1, K2, Ki, Kn, then we can apply the same linear function, the Lagrange interpolation linear function on the shares of K1, K2, Ki and Kn and end up getting shares of AB. And our goal is finally to obtain shares of AB. We do not want to make A public, we do not want to make B public in the degree reduction problem, and we do not want to make AB also public. Somehow we want to obtain shares of AB lying on a random t degree polynomial, and computing shares of AB is equivalent to computing this linear function in a secret shared fashion. And remember, we had already seen that how to securely compute linear functions in a secret shared fashion, right. That was our starting point to discuss the BGW protocol. The simpler case for the BGW protocol was when the inputs of the parties are available with the respective parties and we want to compute securely just a linear function of that. It is very easy to compute that, and that is what is the scenario here based on this observation, and that is precisely what the GRR method does. We want to compute securely a secret sharing of AB as a publicly known linear function of secret sharing of K1 to Kn. Right now the secret sharing of K1 to Kn is not available because K1 is right now not available in a secret shared fashion, it is available only with P1. K2 is not available in a secret shared fashion, it is only available with P2 and so on. But if we want to compute securely this function, that is always possible by asking the respective parties to secret share their private inputs, and the private inputs of the respective parties are now K1, K2, Ki, Kn. We do not want to make the values K1, K2, Ki, Kn public, but still we want to compute the output A times B, which is the linear combination of this K1, K2, Ki, Kn in a secret shared fashion, and this can be done very easily. And why it will be ensured that the final shares of AB which are computed as linear function of secret sharing of K1, K2, Ki, Kn will be a random vector of shares, because that will be triggered by the randomness which is used to securely compute this linear function. Okay. So, now let us see what exactly happens in the GRR degree reduction method based on whatever we have discussed till now. So, we want to securely compute a linear function of publicly known linear function of K1, K2, Ki and Kn, and we know how to, and that is a linear, since it is a linear function we know how to securely compute it. Basically each party has to secret share their private inputs which are K1, K2, Ki, Kn respectively, and since the linear function is publicly known, namely the linear combiners are publicly known, the parties can apply that linear combination on the shares of K1, K2, Ki, Kn and then obtain the respective shares of A. Right. So, we ask P1 to do this, namely it picks a random polynomial k1z of degree t and secret shares k1, namely it runs an instance of summit secret sharing to secret share the input k1. Similarly, P2 will be asked to execute an instance of summit secret sharing and secret share k2. Pi will be asked to act as a dealer and run an instance of summit secret sharing to share ki. So, for that it will be picking a random polynomial of degree t whose constant term is ki, and like that we will ask the nth party to pick a random polynomial of degree t with constant term being kn and distribute the shares. And after we compute this linear function, why we can compute this linear function now, why it is possible? Because the inputs for this linear function, namely k1, k2, kn is now available in a secret shared fashion, and since C1 is publicly known, each party, say the first party, it computes C1 times the first share of k1 plus C2 times the first share of k2 plus C1 times the first share of ki plus C1 times the first share of kn. Okay. Similarly, Pi, it will take all the iths for k1, k2, ki, kn, multiply them respectively with this public constant C1, C2, Ci, Cn, and it will obtain its new share called Ci. And similarly, the nth party, it will take all the nth shares that it has got in the respective secret sharing instances, multiply them with C1, C2, Ci, Cn respectively and obtain this share. And the claim is now that this vector of values, this vector of C values, which now the parties have collectively with ith party having the ith component, lie on a polynomial Cz whose constant term is t, whose constant term is ab and its degree is t, and it is a random polynomial. That means, all its coefficients except the constant coefficient are random elements. Why so? Because each of these polynomials k1, k2, ki, kn, which are picked in the individual instances of summit secret sharing, random polynomials, of course, except the constant coefficients. So, k1 has all its coefficients randomly chosen except a constant coefficient, ki has all its coefficient randomly chosen, kn has all its coefficients randomly chosen, and if you take a linear combination of this random polynomials with random coefficients, you obtain a random polynomial whose coefficient will be random, of course, except the constant coefficient. And why the constant coefficient ab? Because the constant coefficient will be C1 times the constant coefficient of k1 polynomial plus C2 times the constant coefficient of the k2 polynomial plus Ci times the constant coefficient of ki polynomial plus Cn times the constant coefficient of the kn polynomial, which we know is right. So, now you can see we do not have to do a two stage approach in the single stage, just because we want to now compute this linear function, and to compute that linear function anyhow parties have to run instances of random secret sharing. We are now able to do the degree reduction as well as bring in the randomness or the randomization just in a okay. So, let us see a demonstration here, okay. And imagine that our circuit is a simple circuit consisting of just one multiplication gate, A times B, that is what we want to compute. Our t is equal to 1. So, imagine A was secret shared through this A polynomial, B was secret shared through this B polynomial. The parties first locally multiply their respective shares of A and B, okay. But right now they are not exchanging them publicly and reconstructing the function output, because we have to first do the degree reduction, and now since after the multiplication there is no more gate, we have to publicly reconstruct the function output. That means, now our circuit is of this form. A is coming from one party, B is coming from one party, there is only one multiplication gate and then there is a function output y. Okay. So, the parties first secret share the inputs, then they do the degree reduction here and then they reconstruct, because there are no more gates after this multiplication. If there would have been follow up gates after this multiplication, then they would have proceeded with whatever they have obtained at after the degree reduction. Okay. And remember, we had seen in the earlier lecture that if we do not do this degree reduction and directly reconstruct y, then that leads to the breach of privacy, namely the party the corrupt party could narrow down that combinations and what could not be, right, and that is a privacy breach. But now we can show that that is not going to be the case if we do the degree reduction. So, right now this shares 2 0 3 1, they are not publicly reconstructed, they are your intermediate K1, K2, K3, K4, okay, lying on a 2 degree polynomial. Why 2 degree? Because t is equal to 1. So, 2 times t will be 2. So, the parties will do the degree reduction, and as part of the degree reduction we need to know the Lagrange coefficients here. Okay. So, I have worked out the Lagrange coefficients for you here. So, this is the k polynomial as per our notation, and this k polynomial is actually passing through your alpha 1 comma alpha 1 2, alpha 2 0, alpha 3 3 and alpha 4 1. So, your k polynomial passes through these 4 points. Okay. So, that means we now need the delta 1, delta 2, delta 3, delta 4 polynomials here. The delta 1 polynomial will be a 3 degree polynomial, where in the numerator you have first except alpha 1 as the root. So, alpha 1, alpha 2, alpha 3, alpha 4 in this setting we have set to 1, 2, 3, 4. So, you can see in alpha 1 polynomial in the numerator all the alphas except alpha 1 are the roots, and then to ensure that this alpha 1 polynomial evaluated at alpha 1 should survive or give the value 1, we have set the denominator like this. So, you can now see that the delta polynomial at alpha 2 and the delta polynomial 1 at alpha 3 and this delta polynomial 1 at alpha 4 will vanish, but it will survive at alpha 1. Okay. As a result, the first Lagrange coefficient will be the constant term of this delta polynomial will be 4, right. So, remember all the operations are performed over Z5, where the plus operations are addition modulo 5 and multiplication operations are multiplication modulo 5. The delta 2 polynomial in the numerator will have a polynomial and correspondingly the third Lagrange coefficient, and the fourth delta polynomial and the corresponding fourth Lagrange coefficient. So, this C1, C2, C3, C4 they are publicly known. They have got nothing to do with the shares of A, B and the shares of 4 which right now are available with the parties. So, now we know that unknown CC, unknown constant C, not constant, the unknown value C is a linear combination, namely it is C1 times the share 2 which is available with the party 1, second Lagrange coefficient time the value K2 which is 0, third Lagrange coefficient time K3 which is 3 plus C4 times K4 which is 1. But the value 2, 0 and 3 and 1 they are right now the private inputs of the 3 and 4 party respectively. So, we in a secret shared fashion. So, that is what will be done now. So, party 1 will act as a dealer and he will secret share its private input K1 through a 1 degree polynomial. Party 2 will act as a dealer and secret share its private input which is K2 through a 1 degree polynomial. Party 3 will act as a dealer and secret share its private input namely K3 through a 1 degree polynomial, and similarly party 4 will act as a dealer and secret shares its private input k 4 through a 1 degree polynomial. And now we have to compute this linear functions. So, k 1, k 2, k 3, k 4 they are now already available in secret shared fashion. Apply the same linear combination. So, on the respective shares of k 1, k 2, k 3, k 4. So, the parties will individually apply the Lagrange coefficients, apply the linear combination, and then they will obtain the respective shares of C. So, this will be now your vector of shares of C, which will be considered as the output of the degree reduction. And now, in your circuit there are no more gates to be evaluated. Okay. We are considering a function which has just one multiplication gate. So, since there are no more gates to evaluate further, the parties will stop at this point, and it is now time to reconstruct the function output. So, they will make the shares of final shares of C public, and the parties will now interpolate alpha 1 0, alpha 2 1, alpha 3 2 and alpha 4 3, and now they will obtain this C polynomial. So, we will again take the case where P 3 is corrupt, right, similar to what we had done when we saw the same example to understand the challenges associated with the evaluating with the process of evaluating the multiplication gates. So, I have now highlighted in bold the view of corrupt P 3. Okay. So, corrupt P 3 will have the shares of A, shares of B, and whatever shares it obtained during the degree reduction problem, and it itself will be acting as a dealer and secret sharing K 3, and then finally, it will be seeing all the shares of C being made public. So, everything which has been highlighted in bold constitute view 3, and it also knows the Lagrange coefficient because they are publicly known. So, this is the view 3, the question mark denotes they are the unknown values. So, now a malicious P 3 with unbounded computing power would like to infer that okay, the final result is 4. Is it because of the case that A is equal to 1, B equal to 4, or is it because A is equal to 2, B equal to 4, B equal to 2, or is it because A is equal to 4, B equal to 1, or is it because A equal to 3 and B equal to 3. Again, let us recall that if we do not do the degree reduction and directly evaluate it as per the BGW invariant, right, then a corrupt P 3 based on view 3 could combination A equal to 4 share 2 for that unknown A that freezes the A polynomial in her view. And if she freezes B equal to 1, then given that she has seen the share 4 for that unknown B in her view, and that freezes also the shares that the other parties would have obtained for that unknown A and B. Then once the shares of A and B are fixed with respect to whatever hypothesis P 3 is making in her mind, that also fixes K 1, K 2, K 3, K 4. Now, if K 1 is fixed to 0, given that P 3 has seen the share 2 for that unknown K 1, together that freezes the K 1 polynomial that P 1 would have used. And if K 2 is fixed to 3, then when that P 3 has seen the share 2 for that unknown K 2 together with K 2 equal to 3 and her share being 2, that fixes the polynomial that P 2 would have used to share that K 2, and that would have fixed the other shares of K 2 as well. K 3 anyhow was shared by P 3. So, she is not going to make any, and K 4 if it is fixed to 0, that along with the fact that for that unknown K4 P3 has received the share 0, that fixes the K4 polynomial and the other shares of K4 that the other parties would have received. And now P1 will check and now the corrupt P3 will check whether the linear combination, the Lagrange linear combination of these shares of K1, K2, K3, K4 gives you these values, and answer is yes. That is quite possible. Without degree reduction, based on the view 3, corrupt P3 was able to throw away certain values of AB. In the same way, we can, I am leaving it as an exercise, but we can show that means if we do the degree probable from the viewpoint of corrupt P3, and hence the privacy property is satisfied. So, with that I end this lecture. Thank you.